Hi everybody, this is our math project. It's about population growth. Well, the problem is the number of bacteria in a culture is modeled by the function n of t equals 500e at the power of 0.45 times t, where t is measured in years. Let's go. This is the first problem. It says, what is the initial population and the relative rate of growth as a percentage of this bacterial population? Well, we have the function t of n equals 500 times e elevated at the power of 0.45 times t. Well, if this is the initial population, t is equals to 0, and it will be like this, times e at the power of 45 times 0. And this is the same of t equals 500 times e at the power of 0. As we know, when any number is elevated at the power of 0, it will turn something like this. So we have this one times 1, and the initial population is equals 500 bacteria. So this is the answer of the first question. And then, what is the initial population and the rate of growth? As the relative rate of growth as a percentage is this one. As we know, this is the same to say 45%, because it turned like a decimal number, and that's everything of the first question. The second problem, we had a question: how many bacteria are in the culture after 3 hours? Well, we follow the function t of n equals 500 times e at the power of 0.45 times t. So we're going to calculate how many bacteria are we going to have after 1 year, and then we are going to obtain the days and the hours to get how many bacteria are we going to have after 3 hours. So we have n of 1 equals 500 times e at the power of 0.45 times 1, and this is equals to 500 times e at the power of 0.45. We remember that e has the value of 2.7182, so this will be like this: 500 times 2.7182 at the power of 0.45, and we are going to get 1 of n equals 500 times 784, that's 1454, and we solve this, and we're going to have 39,000, no, 392,072.7. Take it here, because we have to get the bacteria per hour. So we are going to divide this over 365 days of the year and over 24 hours of the year, and we're going to get 44.71, and this we're going to multiply to times 3, and we're going to have 134.27 30 and we have to add 500 of the initial bacteria culture, and we're going to have 234.2713 bacteria after 3 hours.
Okay, in this problem, we're gonna see after how many hours will the number of bacteria reach 10,000. First, we have 10,000. No more. Okay. In this problem, we're gonna see after how many hours will the number of bacteria reach 10,000. Okay. First, we have 10,000, and this is equal to 500e times 0.45 t. Then we're gonna pass 10,000 over 500, which is gonna be equal to e times 0.45 t. After that, we're gonna get, that's it right here, we're gonna get 10,000 over 500 ln, which is the logarithm, equals to 0.45 t over 0.45. This will give us t, which is 6.65, which means that it will reach 10,000 in 6.65 hours. Yeah, tú me dices. No más. Okay, so we have t, which is 6.65 years, which is we're going to change to hours, and it's gonna be 58,254 hours for the bacteria population to reach 10,000.
Now we are going to express the graph of the bacterial population function. This is our formula, and I change x for hours and y for bacteria. Well, when the hours is 0, our first point is going to be in 500 because that is the volume of the problem. It will be going about 0.45. The time of the bacteria will be growing, so the graph will be growing about this much, about every 0.45 hours. That will be.
Hey guys, we're here again. We learned a lot about this project, so now we're here about the conclusion. We're going to listen Jose. Tell us, Jose, what is your conclusion about the project?
Okay, our conclusion for this problem is that we know that the population growth of the bacteria kept growing really fast. We know that on 3 hours the population of the bacteria would be 1,928, and we also know on 10,000 how many hours would pass for the bacteria to reach 10,000. That would be 6.7 hours, and and I think that's all. Hope you enjoy the video. We love math.
Love you.
That's all. Kisses,
Hugs, and all that stuff.
That's
See
it.
you.
Damn.